Let me just share my screen really quick. All right. So today we'll be talking about the integral of natural log and some of the properties of a natural log. We'll do a lot of practice with integrals, and we'll talk about some inverse functions as well. All right, so I guess without further ado, let's go ahead and jump into the integral of natural log and how natural log is defined. I guess one thing to note is the natural log is defined by its integral. Or in other words, the way we actually define natural log of x is by saying it's the integral from 1 to x of some function, 1 over t. And this is the actual mathematical definition of natural log, although this isn't like a huge thing you need to know. Really important thing to know is that natural log of u is equal to the integral of 1 over u. And these look really similar because they are, but this is the general form for the natural log. So, for example, we had the integral of 1 over 4x plus 3 dx. Well, we could let u equal to 4x plus 3. Du is 4 dx. So dx is 1 over 4 times du. So then we end up with the integral of, we can pull our 1/4 out, u divided by u. The integral of du over u is natural log. Our 1 over 4 stays out front as a constant. Then we just substitute u back out. And that is our answer. Make sense? Good. All right. So now let's talk about some of the properties of the natural log. All right. Domain of natural log is all real numbers that are positive. So anything bigger than 0. The range is all real numbers. It is continuous. It is also increasing. So we could say it's monotonic. And because it is continuous and increasing, we can also say that it is 1-to-1. This is actually important when we start talking about inverses, which we'll do later on. It is also concave downward, which means that its second derivative should always be less than 0. A couple of important values of natural log. Natural log of 1 is equal to 0. The natural log of e is equal to 1. And one thing you may not know is that the natural log is just basically a special way of saying log base e, which is why the natural log of e is equal to 1, because its base is equal to the value inside. So just the natural log is the same thing as log base e. Additionally, natural log follows all the log rules. So like the power rule, you can bring coefficients out. You can bring exponents out front. Follows the product rule for logs. Split multiplication inside a log to addition outside the log. And additionally, the quotient tool for logs, where you can split division inside the log into subtraction outside the log. All right, do all of these properties make sense? Cool. In that case, let's go ahead and do a few integrals involving the natural log. So here's a few practice problems for you guys. And there's going to be a lot more practice problems today than usual, just a word of warning. All right. First, you guys go ahead and try out those three. And just let me know when you're done. Right, how's it coming? Stuck on C. Yeah, C is a bit difficult than the other two, because the first two can both be solved with really straightforward U-Substitution. The third one requires a little trick. So let's go ahead and go over these. On part A, we can let u equal to x cubed plus x. Du would then be 3x squared plus 1, of course, times dx, which is exactly what we have up top. So you can just make the really simple substitution. It goes right to du divided by u. The integral of du over u is, of course, the natural log of u plus c. We substitute u back out. Natural log of x cubed plus x plus c. Not too bad. Part B is going to be pretty similar as well. Let u equal to x squared plus 1. Then du is 2x dx, or in other words, x dx is equal to du divided by 2. So we end up with the integral of 1/2 u divided by u. All I did is I said that u divided by 2 was 1/2 u, and pulled my 1/2 out front as a coefficient. Of course, the integral of du over u is natural log. We keep our 1/2 as a coefficient, and then we just substitute u back in out. 1/2 times the natural log of x squared plus 1 plus c. That's our answer. Okay. So any ideas for part C? Would a standard U substitution work here? I don't think so. All right, that is correct. Because if we let u equal to x squared plus x, then du would be 2x plus 1 dx, but we don't have a 2x on the numerator. So maybe that's not what we want to do. In this case, I'd like to use a method called partial fraction decomposition. Have you heard of that? No, all right. In that case, this is a nice time to talk about it because it's something you'll end up seeing probably a lot. And basically, partial fraction decomposition is a way to manipulate this inside portion into a way that we actually know how to integrate. So if we factor the denominator, we pull out an x, right? Those are the exact same. But then I'm wondering, because this is product of two different parts on the denominator, we could actually rewrite it as the sum of two fractions, with some unknown numerators, a and b. And then you'll notice if we tried to add these two fractions, a over x and b divided by x plus 1, well, first we would need to find a common denominator. And that would be x times x plus 1. So we would multiply a over x by x plus 1 divided by x plus 1, and b divided by x plus 1 by x divided by x. With me so far? All right. So now what we have is we have 2 divided by x times x plus 1 equals a times x plus 1 plus b times x all over, since they have the same denominator, we can just add them in the same fraction, x times x plus 1. These have the same denominator, so that means that the numerators must be the same as well. We could also simplify this by multiplying both sides by x times x plus 1. It's the same principle, because then the denominators would cancel out, right? But the important thing is we essentially get down to 2 equals a times x plus 1 plus b times x. And we can actually solve this equation because it has to be true for any value of x. Right? This sum of fractions will hold regardless of the value of x. It means we can actually choose specific x values in order to solve for a and b. So for instance, I'm going to choose x to be 0. And we have 2 equals to a times 1 plus b times 0. Since b times 0 is 0, we just get that a is equal to 2. Next, I want my a to go to 0. Although since now I know a, I could honestly use any value of x, but I'd like a to go to 0, so I need to think what x value is going to make this x plus 1 equal to 0, and that would be negative 1. 2 is equal to 0 times a plus b times negative 1, so b is equal to negative 2. Does that make sense? Now, we've actually got our whole format all set up. And we found our a and b values now. So we can actually write, let's see, I don't know if I can do it. Yeah. Let's see. So we've got a and b, and we know their denominators. So we can write that 2 divided by x squared plus x is actually exactly equal to 2 divided by x plus negative 2 divided by x plus 1. Which means that the integral of 2 divided by x squared plus x is the integral of 2 over x plus negative 2 over x plus 1. And of course, we would have a dx on both of those. So now our problem is we just need to find the integral of 2 over x and the integral of negative 2 over x plus 1. And neither of those are too difficult. All we can do, we say, well, the integral of 2 over x dx is equal to 2 times the natural log of x. And then the integral, of course, we'd have a plus c, the integral of negative 2 over x plus 1 dx. We could let u equal to x plus 1. Du is equal to dx. So this is the integral of negative 2 times the integral of 1 over u du, negative 2 natural log of u plus c, which is negative 2 times the natural log of x plus 1 plus c. And then our answer would just be these two parts added together. So we get that the integral of 2 divided by x squared plus x dx is equal to 2 times the natural log of x minus 2 times the natural log of x plus 1 then plus c if we just combine both of our constants. Does that make sense? It's a bit complicated when you first see it, but if you get the general idea, it's usually not that hard. In fact, let's do a really brief recap. What we did is we noticed that we can't integrate 2 over x squared plus x just by normal U-substitution. We could factor the denominator. So because we could factor the denominator, we looked to see how we could split up our large fraction into 2 smaller fractions with simpler denominators. So we said 2 divided by x times x plus 1 has to be equal to a divided by x plus b divided by x plus 1. That means that 2 had to be equal to a multiplied by x plus 1 plus b multiplied by x. That's what we had right here. And then since it had to be true for every x value, we could choose x values in order to essentially eliminate some of the variables we had. So for instance, we could choose x equals to 0 to get rid of b in our equation. And in that way, we can solve for a and b. We simply plug a and b back in to the partial fractions that we found in order to get actual equations that we could integrate and then use as our answer. All right, so that's a pretty nice problem. And probably, but for now, I'd like to finish this integral of natural log section with just a couple more examples, practice problems. So here's the last couple of practice problems for this section. And finally, go ahead and give those two a try. How's this one going? You're stuck? Alright, on which one? E. Okay. Yeah, this is actually a lot scarier than it actually is. I mean, sorry, it looks a lot worse than it actually is. Um, but the thing to remember here is that this E is not actually a variable. Really, it just represents a number. E is a number just like I is a number. They're not the same, so I shouldn't use the equal sign. But also just like 3 is a number. And because it's a number, that means it's a constant in this case. We can actually pull it out front as a constant. Does that make sense? And now this integral of 1 over x dx is just a really easy, it's just the simple form. Use our natural log rule. 1 over e squared, of course, stays out front. We have natural log of x, 1 to 2. And of course, here, I'm hoping you guys remember this notation. Remember when you have a definite integral, we can use the notation a large vertical bar, and on the top is our upper limit, on the bottom is our lower limit. And what that means is we take the top limit and plug it in, function, subtract bottom limit, plugged into a function. Now, the natural log of 1, we talked about this earlier, is just 0. So our answer is the natural log of 2 divided by e squared. Make sense? Yeah. So once you actually start thinking of this e squared as a number, really not that bad of a problem. Okay, did you try e? No, okay. Well, just making a guess. Should we do U-substitution on this one? Yes, okay, good. Now what should U be? Natural log of x. All right, excellent. U would in fact be the natural log of x. And then that would make du equal to 1 over x times dx. Which means, yes, here I can start circling things. It's going to get a bit crowded, but here's our 1 over x. There. Also our dx. So that turns into our du. And then we have our natural log of x as our u down here. Of course, it's 1 divided by u. Then I wrote that du a little too low. Regardless, we have 1 divided by natural log of x, so that goes to 1 over u. And then du. And this is the general form for the natural log of u. then u is the natural log of x. So we substitute u back out, and we get the natural log of x as our answer. Make sense? Yeah, it is pretty interesting. It's especially irritating when your L's and your absolute values look very similar. So be careful with those, because I have gotten confused with that a lot. Just messing up my L's and natural log. Sorry, absolute value signs. All right. I think that's enough with the natural log for now. Let's go ahead and talk about just integrals that maybe aren't necessarily related to natural log. So we'll briefly talk about some trig integrals. Remember, the integral of sine u du is negative cosine of u plus c. Integral of cosine u du is sine of u c. Integral of tangent of u du is secant. That's the derivative. Negative natural log of cosine u plus c. And this is actually accomplished when we rewrite tangent as sine over cosine. And then we can make a U-substitution, and it does end up being in the form of natural log. I believe I talked about that last week, so we're not going to go super into it this week. This is just a briefie for you. The integral of cosecant of u du is equal to negative natural log of cosecant of u plus cotangent of u plus c. Integral of secant of u du equal to the positive natural log of secant, that is secant, I swear, plus, that should just be a tangent of u. Plus c, and lastly, the integral of cotangent. Is not right today. Integral of cotangent of u is equal to the natural log sine of u plus c. Okay, you'll notice that the integrals of cosecant and secant are very messy. You would be right. If you want to see why these integrals come out this way, you can actually look them up. The proof is online, but it's a bit irritating to do. So I'm not going to go into it right now. But these are just a couple of brief refreshers. You should have all of these memorized ideally, although the integral of tangent and the integral of cotangent you might not need to memorize, because you can always just do the integral yourself if you write it as sine over cosine. The integral of cosine or sine. Those ones aren't too hard. But these ones you should all have memorized. As far as the integrals of cosecant and secant, I mean, if you want me to show them to you later, I can do that, probably just after we're finished with this recording, though. Not too terribly difficult, just a bit time consuming, so I don't want to get into it right now. Because there are a couple of things you'll see crop a bit. Yeah. Let's see. Okay. So there are a couple of other methods of integration. One of those we actually talked about not too long ago. That was partial fractions. Another one you might see on occasion is long division. And I'll just go ahead and do an example for long division. Let's say you have the integral of x squared minus 5x minus 6 over x plus 1. Yeah. So I'll notice that a U-substitution won't really work in this case because our bigger term is on top. If we factor, that also won't work because top factors into x minus 2 times x minus 3, so we can't really get any cancellation going on either. So we still need to integrate this, and that's where this method of long division comes in. In general, you want to use long division when this function, this integrand, is either top-heavy. So, for instance, we've got a 2 on top here and just a 1 on top on bottom, so it's top-heavy. Or occasionally when it's balanced as well, and a U-substitution won't work. What we do is we actually perform this division that this fraction represents. And we can do that through polynomial division. Just to clarify, you guys have done polynomial division before, right? Okay, cool. Yeah, polynomial division, it's useful to know. We can actually just go ahead and do this division that this fraction represents. Say, okay, how many x's does it take to multiply x and get x squared? That'll just be x. And again, we would say x times x is x squared, x times 1 is x. And then we subtract this out, so our x squareds cancel, we get minus 6x. That would make minus 6. And negative 6 times x gives us negative 6x. Then minus 6. And we need to subtract that. So that would be negative 6 plus 6 is 0x. Negative 6 again plus 6 is also, that should not be it. Let's see. Oh, maybe I did just factor this out wrong. That's going to be a plus 6. There we go. That should be a plus 6, sorry. And then positive 6 plus 6 gives us 12 as a remainder. You can say this is plus 12 divided by x plus 1. Okay, so that means that this integral has now become the integral of x minus 6 plus 12 divided by x plus 1 dx, because we actually simplified this fraction into a whole part and a fractional part. And we know the integral of x is 1/2 x squared. We know the integral of negative 6, negative 6x, and this 12 over x plus 1. It actually comes out to be a natural log. We can let u equal to x plus 1, du equals to dx. Regardless, we come out with 12 times the natural log of x plus 1 plus c as our answer. That makes sense? Cool. So that is one method for doing integrals. It's especially effective, like I said before, if your integrand is top-heavy or balanced. as far as partial fractions, the other method of integration that I wanted to really talk about today, since I went over it earlier, why don't you guys try this practice problem? And I'll go ahead and give you a few minutes to try that out. It's up to you if you pull the constant out or keep it in. It shouldn't change your final answer though. Usually easier to just keep it in this situation though, since you're going to be solving your equation anyway. Okay, let's see. I'd like to go ahead and go over this. Did you guys manage to find an answer? negative 1 natural log of x plus 1 plus natural log of x minus 1. Let's see. That could very well be it. I actually haven't worked this out yet. Regardless, we know that 2 over x squared minus 1 back to the denominator into x plus 1 times x minus 1 means it's equal to sum a over x plus 1 plus b over x minus 1. What that tells us is that 2 is equal to a times x minus 1. Remember, we've got to multiply this a by the opposite denominator, and of course b by the opposite denominator as well, plus b times x plus 1. Let x equal to 1, and 2 equals to 2b, so b equals to 1. And if we let x equal to negative 1, then our b would disappear, so we get 2 equals negative 2a, so of course a equals negative 1. And what we're left with is the integral. We just replace our a for negative 1, for x plus 1, plus b is 1 over x minus 1 dx. And I'm not going to bother doing U-substitution because I can see that our du would just be dx. And what we end up with is negative natural log of x plus 1 plus the positive natural log of x minus 1. Let's see. That was just a pretty quick run through of example partial fractions. You will see a lot of natural logs in partial fractions, I will tell you that. Well, nice job. All right. Now, for the sake of time, I'd like to talk about inverse functions now. Is that considered algebra, the partial fraction stuff? Yeah, it's just like algebraic simplification. It is basically just algebra, so it's a bit weird to think about though, since it's like kind of going backwards from what you normally do, but it is algebra. Okay, and if we've got time at the end, we'll probably do a few more practice integrals, but for now, we're going to move on to section 3, this review, is inverse functions. Okay, and I guess we'll start with the definition of an inverse function. That is f of x and g of x are inverses if and only if f of g of x is equals x, and that is also equal to g f of x. So basically, no matter what value you plug in to f of g of x, you'll get that same value back out. And this comes with a lot of interesting properties and some conditions that you have to meet in order to determine if a function has an inverse. One of these properties of inverse functions is f and g. Let's see, we'll start with saying that f and g are inverses. Then one property they have is that f is equal to g reflected across the line y equals to x. Let's say we've got just the coordinate plane right there, and we have some function g of x, and it looks like, I don't know, what should it look like? It's going to look like this. Very generic, very basic. Line y equals to x is just this diagonal line. So our rule that f is g reflected across y equals to x tells us that our inverse function would look something like this. That's very poorly drawn, but you could see it in, for instance, the case where y is equal to the natural log of x. The inverse would be y equals to e to the x. Of course, the function e to the x looks something like, this one. E of x, this red line here is already a pretty good approximation of x. E to the x looks something like that. And this way you can a little more easily tell that this is a much better drawing. You can more easily see that, okay, yeah, natural log of x is just e to the x reflected across the line y equals to x. Another way to write this is if you have a point x comma y on on f, that will be the point y comma x on g. Or in other words, if there's a coordinate on f, if you switch those two xy values, then that coordinate will be on g. Make sense? I guess now we'll talk a little bit about when a function can have an inverse, because not all functions have inverses. Function has an inverse if and only if it is 1-to-1. And this 1-to-1 thing basically means that for every x value, there's only one y value. So for example, if we've got a function like this, it would be 1-to-1 because for every x value, there's only one y value. Or in other words, it passes a horizontal line test. In other words, no matter which horizontal line we draw, it's only going to hit our function at one spot. If we had a function that looks like this, that would not be 1-to-1 because we could draw a horizontal line, say here. You see that hits our function in 1, 2, 3 spots. And that is why a function like y equals to x squared, which looks like, just a generic parabola, doesn't have a true inverse because it fails the horizontal line test. We can approximate an inverse for y equals to x squared, but only for like the right half of the parabola, right? Only for the positive numbers, because one of our properties of the inverse is that g of x has to equal to x. So if we took a parabola y equals to x squared, only for x is bigger than or equal to 0, we can take the inverse to be the square root of x. And then we could see the square root of x squared would give us just x. But since we can't have the square root of some negative x squared, that's why we can't have a true inverse, because the square root of a negative number doesn't necessarily exist. Yeah, important takeaway from that whole spiel was the function has to pass the horizontal line test in order to have an inverse. But what if you aren't necessarily given the graph of a function? How do you tell if it has an inverse? Well, in that case, you have to tell whether it's monotonic or strictly increasing or decreasing. Right? Because if you know that a function is always increasing, then it has to be 1-to-1, right? Because you're like increasing. Well, I can't decrease, so I still have to be increasing, which means that no matter where you choose to draw a horizontal line, it's never going to intersect your function more than once. Make sense? Cool. So let's say we had this function f of x equals to x cubed, and we wanted to see, does it have an inverse? Well, we need to show that it's always increasing. In other words, its slope is always positive, right? So we can take the derivative to find the slope. And we have this x squared term here. And what we know is that a number squared is always bigger than 0. So 3x squared should always be bigger than 0, which means that f prime of x is always bigger than 0, which means that f of x equals to x cubed is strictly increasing. Therefore, it is invertible. Make sense? Yes, it would work if it's always decreasing. Because again, it's like the same kind of thing where we had with the increasing function. Remember, no matter where you draw a horizontal line, because it's always decreasing, it's never going to intersect your function movements. In fact, why don't you guys try out this problem right here? Show that this function is invertible. All right, how's it coming? Proving that it can inverse. I would argue that it is invertible. It can have an inverse. And then we want to show that using the derivative. Take the derivative, you could use the chain rule, bring the 3 down, keep the inside unchanged. decrease the power by 1. The derivative of the inside is just 1, so we don't really care. And then the constant of plus 4 disappears. But again, you'll notice that this is a squared term that is always bigger than or equal to 0. Which means that negative 3 times that term is always smaller than or equal to 0. Which means our derivative is always smaller than or equal to 0. So our function is strictly decreasing. Since it is strictly decreasing, we can say it is monotonic. So it has an inverse. Make sense? Cool. Okay, there is one theorem regarding inverses you should know. And of course it starts with if f and g inverses, then g prime of x is equal to 1 divided by f prime of g of x. And this seems really random. We'll actually go over the proof. It's not a very difficult proof. You'll recall from the definition of an inverse, f of g of x is equal to x. This is just from the definition of an inverse. So if we take the derivative of this, we would get f prime of g of x multiplied by the derivative of g of x by the chain rule. We just take the derivative of the outside and multiply by the derivative of the inside. The inside unchanged. That might have been a weird order. Take the derivative of this outside part and get f prime, and we leave the inside unchanged. Lastly, we multiply by the derivative of the inside there. And then the derivative of x is just 1. So then, in order to get g prime of x by itself, we can divide both sides by f prime of g of x. We get that g prime of x is 1 over f prime of g of x. That is the theorem. You might see this pop up in problems occasionally. I don't have an example for this one, but should know this theorem. Okay, I guess we'll move on to other practice problems. Let's see. Alrighty, show that f and g are inverses. You guys know how to show that two functions are inverses? Right, we'll talk about that really quick. So, if you remember, f of g of x is equal to x if and only if f and g are inverses. So that means, in order to show that f and g are inverses, we need to take f of g of x. Right. So what we can do in this case is we can say f of g of x, that's just equal to 5, and then we plug in g of x wherever we see an x here. So times x minus 1 over 5 plus 1. And then our 5 would cancel right there. X minus 1 plus 1, that equals to x. Next, we need to show that g of f of x equals to x But then g of f of x is 5x plus 1 minus 1 over 5. Remember, we just plug in all this wherever we see an x. And negative 1 and positive 1 cancel. We get 5x over 5. Our 5's cancel, and we're left with just x. Since these are both equal to x, f and g are inverses. Make sense? Cool. All right, I think we'll do one practice problem with these. And just show that these two functions are inverses. And then I'll let you guys ask any questions. All right, go ahead and give that a try. Are they equal to negative x? They shouldn't. Let's go ahead and take a look at this since we're just about out of time. If you'll remember, f of g of x will be equal to 1 minus cube root 1 minus x cubed. Cube root of 1 minus x cubed. We'll just go to 1 minus equals 1 minus 1 minus x. Got to distribute the negative, so 1 minus 1 plus x is equal to x. I'm guessing that's maybe where your negative x part was coming in. You didn't quite distribute your negative all the way. In this case, yeah, it's an easy mistake to make, so just gotta be careful about that. For g of f of x, we've got the cube root 1 minus x cubed, which simplifies down to the cube root of 1 minus 1, 0, then plus x cubed, which is just x. So since f of g of x is equal to g of f of x, and they're both equal to x, then f and g are inverses of each other. All right, I'm going to go ahead and stop recording.